Corporate training programs consistently achieve high completion rates, yet routinely yield zero measurable change in how employees actually do their jobs. Look at how an instructional designer typically kicks off a project. It usually begins with a slide outlining the course objectives. Notice the vocabulary used here. The client wants the team to understand computing or appreciate a new compliance protocol. The problem is one of visibility. Understanding is an internal state. Because it has no external physical output, an instructor cannot objectively look at an employee and measure if they have achieved it. Effective learning design discards the abstract goal entirely, starting instead by defining a performance gap, the distance between what a learner does now and what they must execute tomorrow. This gap provides stable anchor points. A traditional goal, floating isolated, anchors to nothing. To fix workplace behavior, we must define the target action, plot the required cognitive mastery, and match the brain's natural pacing. We are not trying to satisfy a subjective feeling of comprehension. We are engineering a structural bridge across a defined space. Consider an organization that needs to teach its workforce how to program in JavaScript. If the assigned goal is to understand the limitations of JavaScript, the design fails immediately. That prompt provides no criteria for what a successful day at the office actually looks like. This table applies a dual constraint test, filtering out invalid objectives. Every goal must pass two questions. First, is this an action the learner performs in a normal workday? Second, can an observer explicitly measure if they've done it correctly? This expanded table evaluates a common objective. Learners should understand project management roles. The constraints expose its weakness. It's extremely difficult to assess if someone understands a role, giving the course creator no architectural blueprint. Returning to the JavaScript problem, we apply the test to a revised, actionable objective. Learner will be able to identify the best programming tools for a specific task and state reasons why. Identifying a tool and stating reasons produces a physical deliverable, a written recommendation, or a verbal defense. It mirrors an exact workplace task, and the instructor can score its accuracy directly. There are rare exceptions. Highly theoretical knowledge, like the foundational math required for nuclear physics, may lack a direct real-world analog that you perform on a Tuesday afternoon. However, even theoretical concepts must eventually serve a function. They exist so the learner can use them to execute a later measurable task. Passing this dual constraint test strips away fuzzy intentions and leaves you with engineerable, real-world behaviors. Establishing an observable behavior is only the first step. The designer must then determine exactly how deep that behavior needs to go. We map this on a two-dimensional matrix. The vertical axis represents cognitive sophistication from Bloom's taxonomy. It scales upward, climbing from basic recall at the bottom, through analysis, up to complex creation at the top. The horizontal axis represents behavioral proficiency, utilizing Gloria-Geary scale. This measures execution, moving from familiarization through conscious effort, ending at automated unconscious competence. This chart plots a specific real-world goal, analyzing electrical schematics correctly. Look at the coordinates. The red X requires reaching analyze in sophistication and conscious effort in proficiency, revealing the true logistical weight of the required training. Pushing learners into the higher, upper right quadrants of this matrix is structurally demanding. It cannot be done cheaply or quickly. Achieving high cognitive sophistication demands interaction with multiple, varied examples. The learner must make errors, receive dynamic feedback, and correct their mental models. Reaching high behavioral proficiency requires significant physical execution, distributed over extended periods of time, until the action becomes automatic. A single 30-minute e-learning module or a one-day workshop will never reach these high coordinates. A single exposure barely achieves familiarization. Deep mastery demands a multi-exposure architectural approach. It structurally forbids the one-and-done mentality that plagues corporate training. Beyond depth and sophistication, different categories of skills operate on distinct temporal timelines. This diagram illustrates Stewart Brand's pace layering, showing how systems mature at different speeds. Outermost layers, like furniture, adapt rapidly to immediate shocks, but the inner foundation changes slowly, retaining history and constraining what can be built on top. we can transpose this exact architectural framework onto human cognition to understand corporate skill acquisition. This table lists the required competencies for a newly promoted restaurant manager. The outer layers represent fast skills. These are tasks with explicit rule sets and definitive right answers, like approving a timesheet or verifying a table setting. Fast skills can be resolved rapidly. You can fix them with surface-level interventions, a printed checklist taped to the wall, or a brief software tutorial. The deep foundational layers represent slow skills. Resolving employee conflict or forecasting seasonal inventory lacks explicit rules. They rely heavily on tacit knowledge and judgment. Slow skills require long-term environmental support. The learner has to see dozens of examples over months or years to recognize the underlying patterns. Matching the instructional intervention to the skill's natural pace layer prevents systemic failure. You cannot rush a foundation, and you shouldn't over-engineer the furniture. Applying a fast, surface-level training module to a deeply rooted, slow behavioral problem guarantees failure. The intervention simply ricochets off the existing structure. All rigorous instructional design discards the illusion of teaching understanding. It begins by locating a measurable gap in real-world performance. Once identified, that target behavior is plotted explicitly on a two-dimensional matrix to calculate the required depth of cognitive sophistication and physical proficiency. Finally, the timeline of the intervention is calibrated to respect the cognitive pace layering of the skill itself. Deploying a quick job aid is like buying a decorative throw pillow. It's cheap, immediate, and highly effective for localized fast skills. But teaching critical thinking is a structural renovation. You have to carefully remove old framing and build entirely new support systems. Attempting to force rapid change onto the slow foundational layers of a learner's personality or cultural background is rarely effective. If the design conflicts with a learner's bedrock foundation, the design is what has to give. To build real competence, organizations must abandon the single-event, comprehension-based lecture. True skill acquisition demands layered, time-distributed practice. Defining observable limits, plotting precise proficiency coordinates, and respecting natural cognitive timelines are the actual mechanics of behavioral change.